First of all, good morning. Thank you to give me the chance to give you this talk. I know that this is not related with the Plone strictly, but the good thing is that at least the technology that is behind of this talk and the Plone sometimes is the same. Then I hope during this talk you will learn something, or at least you will have the chance to learn something interesting. Okay. Basically, the points, first of all, we'll go just a quick summary about me, and then we will try to figure out why Skyscanner choose Aiohttp, why we choose Aiohttp, to put all of us in the same context. Then we will go deeper to the most technical stuff. First of all, we will see how are we tracing the incoming requests. To then see the other side of a microservice that is run on top of Aiohttp, seeing how we call other microservices. Then we will change absolutely of the matter of the question. We will go to how DNS is handled by Aiohttp inside of the AWS infrastructure. I think this is something that can be interesting. And then we will go to some important matter about the misleading timeouts that can be gathered in some situation when the reactor is saturated. I think it's pretty interesting stuff. And finally, we'll go for desired plan or what plans we have in the future to improve Aiohttp, also taking into account that we are trying to run Aiohttp at a scale. Okay, just a bit about me. I'm a senior software engineer at the Skyscanner. I am formerly member of Hotels Attachment Squad. It means that we own many microservices. Between them, we own one that runs on top of Aiohttp. We had the chance to rewrite all of the legacy code that was made using Twisted and change it to Aiohttp. I think was a good experience. Also, I'm a collaborator of the MShell Squad. The MShell Squad is on top of Skyscanner, we have a squad that is responsible of maintaining the formal frameworks, among them the Aiohttp. And also, I am an open sources committer, and this last year I had the chance to contribute to the Redis, Aiohttp, and other projects. Okay, Skyscanner and Aiohttp. Why? Well, basically, Skyscanner is based on an architecture, a microservice architecture. The protocol that is used between each microservice is HTTP. And most of the language used the Skyscanner, Java, JavaScript, and Python, have an official and supported HTTP framework. The adoption of a standard of HTTP framework has some advantage. For example, you can share the knowledge, you can avoid the fragmentation, or we can implement the communalities. This is the main focus of this work, is, okay, let's try to use the same framework, HTTP, let's try to solve the same thing in the same way, because we know that we learn that this is the best way to do it. And why HTTP? And the same question is, why Asyncio? Okay, we were looking for a framework based on IO-bound scenarios, mainly because our infrastructure is in AWS, and AWS uses a lot HTTP REST APIs, for example, DynamoDB, S3, and so on. Also, having a microservice architecture, even the DB are abstracted on top of HTTP REST services. Also, Aiohttp meets the basic requirements that we have. Basically, it means acceptable performance versus commodity, and also there is an active community that is committing new features every day. Also, we believe that right now, Asyncio is enough maturity. Asyncio API becomes stable since Python 3.5. We know that previous this version, the API was a bit broken, but right now, the API is completely stable. And also, reputed Python HTTP service also have plans to use Asyncio. This is the example of Tornado. But not only that, also most reputed repositories like, for example, Request that uses URL lib, they are thinking on move the core from the synchronous to asynchronous one. This is why we choose Aiohttp and Asyncio. But also, we have to face some uncertainties. This is different. The code that you could produce in synchronous. And asynchronous can be completely different. It means different patterns, different problems, and most important, less experience. And also it's true that some libraries might be not mature at all. They didn't have enough time to grow. They have in a small community. They had less feedback. It means that some libraries cannot be in the same level as the synchronous ones. Okay, let's go for the first technical step. It's about tracing incoming requests. Basically, what we need to know is what is happening in our microservice and what happened in our microservice. At least in two levels. First level is about the HTTP endpoints. Every time that we deploy a microservice, that we have many endpoints, we would like to know time per request and statistics about this time, like average, P90, P99, number of requests, status per request, errors, and so on. And what about the access log? We would like to have an historical access to that access log. And if it's possible, index this access log to have, for example, a way to query, give me all of the requests that took more than 20 seconds. And if it's possible, we would like to correlate all of the logs that belong to the same request. That will be amazing. That is are we going to try right now. Basically, first of all, we have a kind of Docker foundations of our microservice to enable this request tracing. These Docker foundations are composed by 4 different elements. We have a front door that is an HA proxy that more or less is the same an Nginx in the traditional stack that you can have in your home. Then behind that, we have the microservice that gets all of the requests that goes through the HA proxy. And this is when the magic starts. The HTTP microservice, as we will see, using a middleware, sends in real time, using the low latency network, per each request, the metrics to a statsd or the logs to Heka that will gather this log and will parse it. Then the statsd and the Heka will use a not low frequency network to send the aggregation metrics to the cloud. In our case, we use, for example, OpenTSDB to have the time series and Elasticsearch to have a way to find the logs that are related for a specific request. Here, the middlewares to rescue us. Basically, HTTP gives you a functionality that it's called middlewares, that is the perfect place to instrumentalize incoming requests. Basically, you can put a piece of code before the handler, and you can put a piece of code before the handler. This is a really easy example. It's basically timing how long this request took, but this is how we implement the middlewares in Skyscanner. And we implement, by default, 3 middlewares: the metric request, the access log, and the correlation ID. Basically, the metric request, we will send statistics per request. The access log will upload logs, and we will see what the correlation does, because it's a bit tricky. Let me show you, for example, an example. Here, for example, this is a microservice that we have in production right now. Every time that we deploy a microservice in Skyscanner, automatically, a dashboard is set up with all of the endpoints, having per each endpoint the number of requests, the average response time, and the number of responses. But not only the average. Also, we are able also to see other statistics, for example, the P90 or other ones like P99. In fact, I encourage you to use not only the average, because it's a tendency, use also P90 and P99, or at least the P75. Regarding the access log, automatically, when you deploy a microservice at the Skyscanner with HTTP, you are able to fill our Elasticsearch indexes with all of the logs, and between them, the access log. Here we have an example of an access log of a line that was produced by our system. The good thing about that is that we are able to index those fields that are inside of the index logs. For example, the time per request. Having that, we can make a request, for example, give me all of the lines in the access log that belongs to the search endpoint and took more than 5 seconds. It's pretty useful because you have a query that allows you to find all of the queries that took more than n time. Then, let's continue with the, Okay, then we have the metrics, we have the access log, but we would like something more. How could we follow the code path executed by a specific request? This is an example. For example, we have a view that logs something, then calls an asynchronous function that it's bar, that logs something, that calls an asynchronous function that logs something else. The question is, how do we can trace all of the logs that belong to a specific request? And here starts the magic. For example, for that, we use a library that was produced by us, that it's called Alió context, that basically stores in the the Asyncio task, keys and values. And then you are able to retrieve these values even when you had a context switch. This is really quite similar to the thread locals that are used by Flask or by Flask. Thanks to that, we can create a middleware that gets from the headers the request ID and saves in the context this context ID. Then, at any point of our system, we can retrieve this information. How? Basically, installing a log filter. It means that every time that we call the logging function, automatically a new field will be created called correlation ID that will have the request ID that was sent by that user. And configuring properly the format, sorry for the brightness, but configuring properly the formatter, we can put the correlation ID also as an output. Having that, we have the chance to log automatically, implicitly, the request ID that belongs to a specific code path. For example, if we go to the previous demo, where we were looking for requests that took more than 5 seconds, we can save this information that is indexed as a new field. I can copy, I can go to here, and I can go that. And then what I will have here is the log produced by this request. Here are all of the logs that were produced for this request. Among them, we can detect at some point that one of the microservices that we call took almost 7 seconds. This is a good way to try to debug your slow queries. Okay, move on. Okay, we are in a microservice architecture. It means that to build complex things, we have to call many microservices. For example, we have an endpoint that has as a param currency, and we need to validate the currency, but we don't know if this currency is allowed or not. To do so, we call another microservice that just do that, check if this currency is allowable or not by our system. If not, we will return a validation error. Therefore, we are keen on also trace all of the calls that are done to an external microservice. And this is the same as before. We want the time spent per request. We want the statistics average, P90 and P99. We want the number of requests, and we want the status code per errors. Also, an example here, for example, this is a microservice that is called from another microservice, and here you have automatically, when you deploy a microservice in a Skyscanner via Aiottp, the amount of requests that you made for this microservice, the average time, and you can see also the average time is split by region, and so on, and so on, and so on. Therefore, we have a full well-coverage metric microservice. Unfortunately, Aiottp does not support by default the request tracing yet. We are working on that, and to do so, what we have to do is publish a new class that is called metrics client that basically overrides the most important method that is the underscore request to put some code before the request is done and after the request is done. Basically, this is all of the magic. Okay. Since here about metrics and tracing, let's change the subject. Let's try to investigate, or let's try to know how DNS in AWS and with Aiohttp we are working. First of all, AWS has its own requirements. From the point of view of a microservice, when you deploy a microservice, usually this microservice is behind a load balancer, an elastic load balancer. It means that when you make a DNS query for this load balancer, the AWS guys, they recommend you to have a TTL of 60 seconds. This is because the load balancer can grow or can decrease, taking into account the traffic that will come into that microservice. That's pretty amazing, but before HTTP version 2, it didn't work. The version 1 of HTTP cached forever an entry in the internal DNS cache. Because of that, we implemented a new implementation of a DNS that, lucky of us, right now is the official implementation that basically meets the requirements of AWS. We have a keyword that allows you to set up the TTL that will be used by the DNS. This is an heuristic value. We don't gather this value from the DNS answer. The question is why we don't gather this value from the DNS answer. This is pretty easy because the current RFC of the libc doesn't give you a straightforward way to do it. It's right that you can do it with IODNS, but with the libc, with the get host by name, it's far complicated. We end up having this value as a keyword. But aside of that, once you have a hit in the cache, the system tries to do a round robin using all of the IP addresses that were resolved by the DNS query. This is something that matches perfectly with our AWS infrastructure. Another quite interesting thing about the DNS is about the dogpile effect. The dogpile effect is basically when you have a miss in the cache and you have 100 records that are incoming altogether, we will try to get this value from the cache. In the case of the DNS, this is the same effect. If you have a miss in the cache and you have 100 records, in this case we have an example of a task that tried to validate the currency 100 times all in the same time, all together, then we will have by default 100 DNS queries. This is not so far the best solution. For that, we implement a feature that tries to throttle all of the DNS queries that try to resolve the same host domain at the same time. This is implemented using an object that it's called event result or error that basically inherits from the event asynchronous primitive. That basically what it does is try to figure out if there is an incoming request in the DNS that matches for that host. In that case, yell from this event, and when the event is done, it uses the value that has been cached. This is also implemented right now in the HTTP.3 that was published yesterday. More things. Misleading timeouts and the reactor saturation side effect. Okay. When we are calling services, we have to be protected by timeouts. What does it mean? If we call the validation currency microservice, we cannot wait forever. We need to put some countermeasures, some other ways to try to handle the non-happy path. Okay, this is, for example, an example. If I call the currency microservice with a timeout of 1 second, if I had a timeout error, I will forward back to the user or to the intermediate layer in the network a 500 for error. It means that the user, for example, can try the same request to another region, or the intermediate layer automatically and magically can try to do it for you. The problem is the timeouts can be misleading. When the reactor is saturated. When the reactor is saturated, the timeouts can be triggered, and it doesn't mean that the network package never arrived to the destination or the network package never arrived to the source, it means that basically the reactor wasn't able to attend the network function during that time period. Then, this is an example of how the timeouts are implemented by Asyncio and also by most of the libraries. Basically, we have a function that is called request that basically instantiates a future and then schedules a function that is called cancel future that we will call after 2 seconds. It means that after 2 seconds, the reactor will cancel your call path for this asynchronous task. Therefore, when the reactor is saturated, sometimes the timeouts can be triggered without being related with the network stuff. Therefore, let's try to monitor the reactor saturation. How? How can we do it? Basically using a technique that is called lack of a scheduled function. This is something that comes from Node.js. It basically says, okay, I have a function that is called lack, and I will call it at each 1 second. 1 second, 1 second, 1 second, 1 second, 1 second. When the reactor is saturated, what will happen is the time that this function will do will be higher than 1 second. And how much higher means much saturated is our reactor. On our right, we have an example of the stack queue of the Asyncio, where at the bottom we have the lag function, and in the top, as more priority one, we have many functions. Therefore, as many functions we have before the lag function means that more saturated is our reactor. In fact, we try to monitor this metric, having also a dashboard for that. This is an example of the last, I don't remember, maybe yesterday, that we had an incident in one of the regions. You can see that most of the time, the lag is almost stable. It's steady to 1 second. But at some point, it increased a lot. It was crazy. Why it happened? Because we lost the half of the instances in that region, and the reactor for the other half got completely saturated. And this is a metric that is really useful to follow. Okay, desired plans. What we have for the incoming future. We commented that in Aiohttp we don't have a way to trace the events that are sent by a request internally. We are working on that. We would like to trace also the queued operation. It means that Aiohttp, when you have a client session, first of all, you set up a pool of connections that has a limit. When you reach this limit, the operation gets queued. And only when there is a free and available connection, these connections gets unqueued. This is pretty important because you have to know that at some moment Aiohttp is applying some kind of back pressure in your microservice, and we would like to monitor that also this metric. But to do so, we would like to implement first a good and well-designed trace system in Aiohttp. This is what we are working on, and also very related. I think the AWS X-Ray for Python was released 2 weeks ago that supports also asynchronous environments. We would like to also to implement another middleware that will help us to put all of these metrics not only in our dashboards, in our OpenTSDB instance, also in AWS, but not only for the records, also for to trace the calls to the third service. And finally, something that we have also in our plan, in our backlog, is about the back pressure at HTTP layer. This is something that can be used to try to scale horizontally when you have a lot of pressure in your systems. It means that you want to start to reject some requests when your system is saturated. This is completely related with the metric that we have seen, that you saw before, the reactor saturation. If we detect that our reactor is saturated, we can respond to the user with a 504 to the user or to the load balancer saying, okay, I'm saturated, but maybe you can add them again in another instance. And obviously, it allows us to scale horizontally when there are a flood of 504 errors. Okay, that's more or less, this is basically the presentation. It was 25 minutes. Questions, please?
Any questions? Thank you very much so far.
Hi. Thank you. It was a really, really good talk. I was wondering if you had any thoughts on debugging tools for async I/O and your experience with trying to debug code in issues.
Yeah. First of all, the default tool that is the PyDebug works pretty good. You can use it. And also you have line profilers that are completely, that supports async I/O since the Python 3.5 version. Then you should be able to debug an asynchronous framework in the same way as you debug a synchronous framework. It's not completely, let's say that the complicated part of debugging an asynchronous framework is not the debugging by itself, is understanding when the bottlenecks are. But this is another matter of question. For that, what I would recommend you is always try to stress your system. Try to stress your system and gather all of the metrics that you can. And then you should be able to figure out where is your bottleneck. That's my experience.